It is now my great pleasure to give the floor to Gerya, professor at ETH Zurich, one of the leading places for earth sciences in Europe, absolutely pioneering in geodynamics, but he has gone a step further. He has gone deeply into biogeodynamics, and this is basically now a very interesting domain of frontier research. So Taras, we look forward to your presentation, and I'm sure there will be some questions after your talk.
Thank you very much, sir. Thank you. So, good morning, ladies and gentlemen. What I would like to do is to make you familiar with this new, rapidly emerging and evolving science, which is biogeodynamics, and then draw some implications for our human civilizations. How should we think about ourselves on a very long-term and large scale? And how should we behave to correspond to unprecedented challenges and opportunities which this new science opens to us? Biogeodynamics is a bottom-up initiative very clearly born in Sopron in 2023. As a result of community brainstorming, we realized that we need community effort to enable emergence and rapid maturation of the new science, which brings together quantitative knowledge about how evolution of the deep Earth interior down to 3,000 kilometers deep, coupled to the evolution of the Earth's surface, Earth's landscape, Earth's life, climate, ocean, and atmosphere. And recently, understanding is that human society and human civilization is globally also is heavily involved into the biogeodynamical cycles and should become an intrinsic part of this biogeodynamics. This may sound to us as a mission impossible because such a complex and dazzling relationship to a first look is very difficult to intuitively, quantify and unravel. But the reality is the following. In all related disciplines, which are listed here, geodynamics, geomorphology, so essentially science about landscape, climate and atmosphere science, geobiology, ecology, and even in social sciences, we now have quantitative tools and quantitative observational approaches that can actually be brought together in a concerted manner to understand how Earth, life, and humans are working together. So this is not mission impossible, but this needs to be really a bottom-up initiative by bridging together sciences that traditionally evolved in isolation from each other. So we did not have, until very recently, lots of relationship and collaboration between, classical biology and ecology with classical earth sciences such as geophysics or geodynamics. But now it's a pending necessity that we have to build these bridges, and for that we essentially started this new networking initiative, which is called EuroBIC, abbreviation from Pan-European Biogeodynamics Network. You see QR code if you are interested to understand what we are trying to do. We started being from 18 countries. Now we are more than 30 countries involved, more than 140 people coming from all different domains, not only from earth sciences, but also from social sciences, from biology, ecology, climate, and atmosphere sciences. We are trying to build this new science and new bridges with the funding generously provided by the European Coast Association for Science and Technology. These are really seed money to promote collaboration on the key research and networking topics involved into this new emerging science. So it's an emerging scientific field, and it faces many challenges. And these challenges are now listed here. So as specific challenges of European action. And the first challenge is, of course, networking challenge. We have to bring together very different communities which are traditionally was not working together. They were not applying together for funding. They do not have the same language. They do not have the same terminology. We do not have a textbook to be common for all these different fields, and we have to bring these communities together. And this is what is the responsibility of the working group 1, networking. Educational challenge is the further challenge. So we have to develop new generation of native biogeodynamicists that have a view and outlook for all these neighboring fields, are familiar with their traditions, knowledge, and culture. And this can only be done by educating new generations and also by educating senior scientists to work together and to collaborate and to understand each other. So one of the responsibility of the educational challenge group is to build the first textbook in biogeodynamics, which will also be accessible for school teachers so that they have this holistic view on Earth, climate, biology, life, and humans, so that we have essentially properly educated community, which will also be very useful for the mental health of the community to see themselves in a bigger perspective. So we see ourselves as a part of the Earth system, which is evolving through millions and billions of years, and then we should not be scared for short-term changes in such a drastic manner. So then, also what is very important are methodological challenges. So we have to use quantitative tools from each other, and this is the responsibility of methodological challenge group, working group 3, tools. Public awareness challenge, as I'm saying, we have to educate public. We have to let public understand how Earth works on a long scale as a whole, as a system, not only collect knowledge in isolated manner from individual fields, but have this concerted view on Earth. And this is what working group 4 is responsible for. Then research funding and manpower for this cross-disciplinary field needs to be generated. We have to find funding tools which are available to us and help creating new tools for funding this very cross-disciplinary research effort. And this is now responsibility of the future working group 5, create space for the future of biogeodynamics in a very practical manner, that funds are available for this very cross-disciplinary research, which does not fit so easily into, subjects-oriented current research tools and funding tools. Then societal challenge, unexpectedly, even to ourselves, this is a big field for societal implications of biogeodynamics. There are things that are absolutely crucial to understand, to just see our role in the, in the evolving Earth, in our evolving solar system, and even on a larger scale in the galaxy and in the universe. And these are all direct consequences of the knowledge that biogeodynamics is offering. And this is what Working Group 6 Society will be doing within this initiative. And then big picture challenge, we have to keep coherency between all different fields. And also we have to think about strategic goals. And then this is the responsibility of the Biogeodynamics Council, Working Group 7, which will take care about the big picture and about strategic thinking and planning, so that all things goes in a concerted manner and coordination is achieved between all these working groups. So, as I was saying to you, unexpectedly, we found out that we have a lot of things to say to the society from the point of view of biogeodynamics. And here I listed 3 theses that may be sounding quite new to you, which are direct implications of recent biogeodynamical research. And these theses are: we are most likely alone in our galaxy as the only intelligent species, and our galaxy is as intelligent as we are, so we should not expect to find anybody in the nearby surrounding. And the mental health of human being is the mental health of the galaxy. So essentially, we are responsible for our galaxy based on what biogeodynamical research suggests about availability of conditions for developing intelligent life and civilizations. And I will try to show you arguments for this thesis. So I am not pleased at all by the fact that I am, responsible for the galaxy, but we are scientists, we have to face challenges, and we have to, believe what our science is telling us. Thesis number 2, based on what the thesis number 1 says us, the primary task of human civilization is to ensure its longevity. So we have to survive on a very long time scales comparable to biogeodynamical cycles for the simple reasons that we are so unique and important for the galaxy and for the universe that we have to think very carefully about our own survival. So any other task that you can imagine will depend and is subordinate whether or not we will be living long enough as technological communicative civilization. And the thesis number 3 is the following. Human civilization is already very deeply involved into biogeodynamical's global cycles. This is the key to understand. We are deeply involved and are in control of some superficial parts of the global carbon cycle. And we have to adjust to the physics of its parts, of the deep Earth interior, of the atmospheric physics and climate physics, which we cannot control and unlikely will be able to control in the future. So we have to really behave in an educated manner, and our climate policy and carbon cycle policy should have longer-term perspective comparable to timescales on which climate change was happening in the deep past, and therefore deep past is the key to the future. So we have to learn from the Earth's history to behave as educated, civilized species. So now let's discuss these first 2 theses about our uniqueness for humans, intelligence in the galaxy, and for the longevity of human civilization. So there is simple fact. We are not systematically contacted by aliens, and we see no signals or no proven presence of other intelligent species in the nearby environment. And then we can ask ourselves as scientists, why is that and what should we do? Here is the spoiler, why is that? Because conditions for intelligence are so rarely created in the galaxy. For the developing of complex intelligent species, we need as a minimum a combination of 3 things. Plate tectonics on a planet, which is providing continuous changes and stimulate complex organisms to adapt and evolve, so to make further and further biological innovations. Second, we need coexistence of continents, means dry land, and oceans, deep water. So, and these should happen on the same planet. An unfortunate fact that biogeodynamical calculations are showing that such conditions are extremely rarely achieved. Much less than 1% of all planets suitable for any primitive life can actually have these conditions coming together on the long time scales necessary for intelligent species development. So what should we do about it? Very simple. We should search for such planets in the nearby surrounding. We should not wait to be contacted by anyone because most likely there is nobody around. And then, of course, we should ensure longevity of our own unique civilization. So this is why we are holding this unique responsibility and facing this unique challenge. So if we think about communication, we should consider the following. Our galaxy is approximately 14 or 13.5 billion years old. Within the galaxy time, there were many episodes of star emergence and planetary system evolution. So stars and their planets are emerging in different times, which is shown by these blue arrows. And then, so they are not moving simultaneously in time. The trouble with this is the following. When we are thinking about intelligence and the presence of life that we can communicate with, probably some planets in our galaxy, and there are many of these planets, they developed, civilizations in the deep past, but this is not useful to us because they become extinct with time. So probably there will be some other civilizations after us, some billions years later, but they are also not useful. We cannot communicate with them unless leaving them messages. We can only directly communicate with civilizations which have their longevity windows shown here by red. So actively communicative civilizations overlapping with our own longevity window. And the broader is our longevity window, the better are our chances to intercept with anybody at all. And this situation has been quantified for the first time by Frank Drake in his very famous Drake equation raised in the 70s, where instead of considering all stars with all planets in the galaxy, he only took subset of these planets which are at the same stage of their evolution. And this can be made by taking this longevity window, multiplied to the star formation rate, R star. We multiply it to L longevity window, and we have stars which are much, much less than the total amount of stars, which are essentially at the same stage of development. Then we find out how many planets are around these stars, how many planets are suitable for life, potentially, and then there are these three probabilities, FL, Fi, and Fc shown in purple. So first probability is, if planet is suitable for life, how big is the probability that life will emerge? And it was estimated, so if planet is suitable for life, sooner or later, life will emerge. Probability is 100% or 1. So second probability, if there is primitive life on a planet, how big is the probability that it will evolve into intelligent life? And again, it has been assumed, since it happened on Earth, then if you wait sufficiently long, sooner or later you will obtain this intelligent life, and then this probability is also 1. And then the last probability is how big is the probability for intelligent life to become communicative civilization, and that one was considered to be less than 1 for a very simple reason. On Earth, there were several civilizations like Maya or Roman, but they were not at the technological level of communication. So probability is less than 1. The trouble with this parameterization and evaluation of the values within the Drake equation is that the number of computed civilizations ready to communicate with us in our nearby environment, like in our galaxy, was from around 200 to 50 millions. Then this Fermi paradox came around. Where's everybody? If there are so many, if there are even on the lower limit around 200 or order of magnitude from 200 to 1,000, so why don't we see systematic signals from them? And this is known like Fermi paradox. The answer to this paradox, in our opinion, can be found in biogeodynamics, and it's very simple. Parameterization is correct, however, estimates for individual parameters is wrong. They are overestimated. For example, here we focus on parameter Fi, what is the probability to obtain intelligent life on a planet with any life. So what we suggest is much, much less than 1. So because intelligent life and civilization and technology require special conditions. And I was outlining these conditions: plate tectonics, continents, and oceans. Second wrong estimate is the longevity of civilization. The upper limit of it was estimated as 100 million years. this is likely at least one order of magnitude too large estimates. So now let's discuss these individual parameters. How can we estimate Fi? So what we suggest, we can estimate it by taking care to compute probability of having plate tectonics together with continents and oceans on the same planet with primitive life. So essentially Fi is the product of two probabilities. One is probability of having plate tectonics, another is the probability of having continents and oceans all together. So trouble with having this opinion that primitive life will always evolve into the intelligent life is the following. I call it 1,000-step problem. You have to go upstairs 1,000 steps, and each step take certain amount of time. And you cannot do less than 1,000 steps. This is exactly the problem. You start from microbe, and then you have to evolve toward human-like species. This cannot be done in one step. This can also not be done in 10 steps. You have to do likely many hundreds or thousands of evolutionary steps, and each step take a long time. And how long? Typical time scales many millions of years. Even in the most kind of fortunate case, like on Earth, which is accelerated by plate tectonics, rising mountains, creating new straits, and forcing species to adapt and evolve, you have to make 1,000 steps, and length of each step is 1 million years. You are immediately at 1 billion years. Imagine unfavorable conditions, 10 times slower, 10 billion years. Then you are nowhere because planets are not living for that long in habitable conditions. So many planets may have primitive life, but only few planets will evolve toward this complex, intelligent life for very simple biological reasons. Look, at the horizontal axis on top of this diagram. Distances between different species or groups of species in time are many millions of years. Typical speciation rates or origination rates are less than one new species per million of years over one old species. So, and you have to make, this biological innovation, many hundreds of them, and you only have limited planetary lifetime for that, and then essentially acceleration of this process is extremely important. And this is where, subduction and plate tectonics and this evolutionary style that we have on Earth is coming around. So we are building mountains. Mountains are changing habitats, and species are in continuous evolution. They are forced to evolve by the interior evolution processes which are affecting surface and landscape and climatic conditions. So there is also climate amelioration, oxygenation of the mantle and atmosphere, enhanced nutrition, and lots of other things that are characteristic for plate tectonics and are not characteristic for other very common styles of planetary evolution, as for example, non-plate tectonic style of Venus. And then what we also observe, present day episode of plate tectonics started 1 billion years ago, and this is also period corresponding to accelerated evolution of complex life. It may look like a coincidence, but likely is not. So how big is then the probability of having plate tectonics on a planet with a primitive life? This can be relatively easily computed by using two very well-known facts that plate tectonic needs sufficient driving vigor, and this is only possible on sufficiently large planets, significantly larger than Mars. Unfortunately, only half of the planetary population, they have sufficient size to drive plate tectonics, so we are immediately halvening these primitive life planets and only taking the bigger ones. In addition, planetary compositions and related, driving forces in a planet are strongly dependent on the stellar composition. And through volatility trend, it has been shown that only 1/3 of all planets, they have capability of hosting plate tectonics and any buoyancy-driven tectonics. Why? Because planets with too many much of light elements, they're simply not creating negatively buoyant plates which can sink into the mantle, and then plate tectonics will not be operating. So then we multiply 1/3 to 1/2, and what we obtain is 17% or less. So this is an absolute upper limit for the estimate. The situation with coexisting continents and oceans is even worse, because dry planets are not good for the beginning of life. You need deep oceans, and you need essentially water-rich environment for the origination of life, and then structural support, protection, nutrition distribution, primitive life like ocean. On the other hand, civilizations, they can only develop on land where you can develop technologies. Radio, fire, electricity is unthinkable in water-rich environment when there is no dry land. So water-rich worlds are probably very common. They are not good for evolving into intelligent life and civilizations. So then, essentially, water-rich is not good, water-poor is not good, water is good. You know, when we have dry land emerging over oceans, and unfortunately, these conditions are extremely rare. You add a little bit more water to the planet, and then all continents are flooded. You remove a little bit too much water from the planet, and then plate tectonics will stop, because you will stop hydrating plates, and then there is no oil in between plates, or better to say water, and then plate tectonics ceases. So you can only vary amount of water by few kilometers compared to Earth, because topographic variations are independent on planetary size. So if we look for all possibilities to create planets with different amount of water, you find out planets cannot control how much water they will receive. And then within this logarithmic range shown in the bottom of the diagram, you see this pink window of appropriate amount of water. So only much less than 1% of planets will receive amount of water which is appropriate. So then we are multiplying two small probability to one another, and we are coming with depressing numbers, which is what telling us that we are alone in our galaxy. So we are really alone. We have to face this challenge, because future estimates of this will only be worse. If you incorporate other requirements, things will not improve. They will actually can only get worse. So now we modify Drake equation, and instead of Fi equal 1, we put Fi much less than 1%, really drastically less. So what about longevity? Longevity was originally estimates up to 100 million years, but this was wishful thinking, because if we think about objective reality, there are two limiters. One is simply species survival, and that one is from some 1,000 years to some million years, up to probably 10 million years. Species can live on Earth. Even much worse things is coming from the societal collapse, because society, they are not eternal. They have their driving power, but they can become essentially collapsed for very simple reason, because population growth does not correlate with resource availability. For non-technological civilizations, characteristic, demise time is some hundreds of years. We have to really face the challenge that our human behavior is to large extent inherited from our biotic nature, from animals' time, and this behavior is in contradiction to the stability and longevity of our human civilization. This land control, growth of the population, and all other things are not necessarily consistent with the longevity of technological civilizations. And we have to study this, we have to understand it, and we have to ensure our own survival, at least on the biological time scale, so biogeodynamical time scale, up to this upper limit of species survival. And this is not a trivial challenge at all. We have to start thinking about millions of years, which is very non-trivial and very non-natural to us. We are thinking about years, probably centuries, millennia, and this is 3 orders of magnitude, too short-term thinking for us in a biogeodynamical context. So because species are evolving on these time scales of millions of years, which are again controlled by the landscape evolution, so habitats formation and destruction is happening on exactly these time scales as recent biogeodynamical studies are showing to us. So now we are putting together all numbers, and what we obtain, probability of having civilizations in the nearby surrounding ready to communicate with us is anything from 10 to -4 to 10 to +4. Middle line within this logarithmic range is 10 to 0, which is 1 civilization at best per galaxy. So this is why I'm saying, you know, unavoidably we are responsible for the Milky Way, and unavoidably we have to think of our own survival. Now, about involvement of human beings into biogeodynamical cycle, and then essentially what we have to do about it. So biogeodynamical cycle is shown here, involve plants, involve marine environments, and involve atmosphere, ocean, involve weathering, landscape, and involve interior evolution. And computational tool has recently been created, and what they are showing, after big emissions of CO2, essential relaxation of the climate is dictated by the plant's ability to migrate within the landscape. So time scales of these evolutions are hundreds of thousands and millions of years. So it's very naive to expect that in such very inertial systems, we can apply some short-term measures and they will lead to the desirable result, because the system is extremely nonlinear. Geographical context is very important. Unfortunately, our present-day geography is not the best possible geography for having, you know, rapid climate amelioration after, you know, CO2 pollution into the atmosphere. So our climate policy, they have to involve this long-term context. There were episodes of global warming in the past related to extreme volcanism, rapid releases of volcanic gases, and they all produce relaxation on hundreds of thousands and millions of years. So this is what should dictate our policy for the present day, and, you know, simulation for present day is not different. So we can probably control CO2 content in the atmosphere, but this is not the only element of intrinsic physics involved into the climate evolution. Climate evolution can have several steady states for the same amount of CO2 in the atmosphere, with the difference between this steady state some tenths of degree, warm, cold, or intermediate. Imagine now we are at this intermediate state. We added CO2 into the system. We obtained this global warming. And then we start to decrease CO2 in the system without being able to control atmospheric temperature. So what we will be doing with that on a rapid term, we will migrate from the mild state toward the hot state. So, and this long-term context must have been taken into account in our long-term climate policy. What if our, net zero CO2 for 2030 will not work? We have to prepare to act on much, much longer time scales. So here I'm coming with my conclusions. 3 theses you have seen already. And the last thesis that follows logically from what I was presenting is the following. We need serious science, which we can call future dynamics, which should actually think about ourselves on the much longer time scales. So we have to build this science, we have to incorporate social sciences and natural sciences, and hopefully we will succeed. Thank you very much for your attention.
Thanks, Taras, for a great talk. Very, very fascinating, and I think time will never be the same again.
Sorry to be over time, but I just
No. This is wonderful, and I think this is so fascinating that we really look forward to the further follow-up. And you showed a lot of brand new results. So I think this is an example of something, and that is beyond expectation. And, well, I think it's very clear that a lot of young researchers will be attracted to this field. We have time for a few questions to Taras, please. Yes, Tom.
I'm just flabbergasted in almost every case at the huge range that you have. Now, either you can say this is a great opportunity for research, or you can say, well, we have nothing tangible.
Yes, you're absolutely right. So you can either be fully disappointed by this, time scale and, space scale, which are not really usual to us as human beings. However, of course, we can build new knowledge. And new knowledge, in my opinion, will bring new opportunities. But in my opinion, we have to rethink ourselves very carefully, because we have to also change our own education. And in my opinion, this will also contribute to the mental health of our society. If you see yourself in a big context, you feel much safer. We are scared very often by this rapid climate change. We think it's a unique situation. We don't know what to do. These big contexts bring us knowledge and opportunities to consider this, that it's not anything new. It's actually intrinsic to Earth, and we can learn it and can probably develop something that will help us essentially to keep surviving on this planet. Survival is not automatically guaranteed, but there is a guarantee if we increase our knowledge, then our chances will be better. Thank you. This is a great question.
One more question. Yes, please.
It was a great talk. Thank you very much. It was fascinating. So in the end, I could think carpe diem. So enjoy the life how it is. But how can you imagine that the artificial intelligence, which we hear about day by day, can accelerate the development in that sense that we are not self-destructing, but improving our mental health?
Absolutely, yes. Artificial intelligence is one of the tools that may potentially facilitate understanding and dealing with this complex system. And for example, the societal models that I was showing for rise and demise of civilization, they already include machine learning and artificial intelligence. I think, big help from these computational tools can be, potentially obtained, and this can become an intrinsic part of this future dynamics research, which will hopefully emerge and actually, make many people more happy, feeling more happy than they are currently. Thank you.
Thanks again, Taras.
Thank you very much.
It's fantastic.